I wanted to make a quick video to help you guys get ready for this Chapter 4 test that we have coming up, specifically the one without the proofs on it. So here's a list of kind of the 5 big ideas from Chapter 4 that you're going to need to know in order to succeed on that test. First of all, we started off by learning that if two triangles are congruent, it means that all their corresponding parts are congruent. And then we looked at 5 kind of shortcut ways of proving two triangles congruent: side, 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 angle, side, angle, side, angle, 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 side, and HL. Now these are the only reasons that we've learned that would make two triangles congruent, these 5 things. Then we took a look at some isosceles triangles and 2 theorems that involve isosceles triangles, theorems 4-1 and 4-2, where 4-1 said that if two sides of a triangle are congruent, then the opposite angles are congruent. And theorem 4-2 just did the converse of that. If two angles of a triangle are congruent, then the opposite sides are congruent. Then we looked at some definitions, some things that you're going to need to know for the test. An angle bisector, of course, that's actually something we've looked at before. But if we were looking at a triangle specifically, if we, the angle bisector of one of the 3 angles in a triangle. The median of a triangle, which connects, remember, a vertex to the midpoint of the opposite side. An altitude, which connects the vertex to, goes to the opposite side, perpendicular to opposite side, and sometimes the opposite side extended, right? Sometimes an extended version of the opposite side. And then the perpendicular bisector of a segment, which does both the things that it says there. It's perpendicular to a segment and it bisects, right? That's why it's called the perpendicular bisector. And then theorems 4-5 and 4-7 dealt with angle bisectors and perpendicular bisectors. This one said if a point is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. And theorem 4-7 says a point on the angle bisector will be equidistant from the sides of the angle. So let's take a look at a few examples that kind of put some of this stuff into perspective for us. First of all, if I have this diagram right here, and I told you that these 2 triangles are congruent, then you should be able to complete statements like the following 3 right here. So if I tell you that these 2 triangles are congruent, and then I want you to tell me that triangle STW is congruent to this triangle right here, we can't just put those letters in any order, remember. We have to put the part of this triangle that corresponds with angle S, we would have to put it first, since we put S at the beginning of this triangle's name. So what does it look like corresponds with angle S down here? It looks to be angle Q, right? So we would put a Q there, and then corresponding with T, right, corresponding with this angle appears to be angle P. So that would be the next letter in this other triangle's name, and then that would leave whatever corresponds to W coming next, which looks like would be R. And then if I wanted to say, well, what angle is congruent to angle R? What part of the other triangle corresponds to angle R? Like we just said, it would be angle W. And then this says blank is equal to the distance from R to P. So the distance from R to P, if I look up here at this statement that I just made up here, I can actually find this answer up here. R and P are the 3rd and 2nd letters of this triangle's name in my statement. W and T are the 3rd and 2nd letters of the other triangle. So it would be equal to the distance from W to T. And so this is just drawing on that idea that when triangles are congruent, then all of their corresponding parts are congruent. Then if we wanted to apply some of those reasons why we can determine triangles are congruent, we might see something like this. So I have 5 examples here. Let's call it example A, B, C, D, and E. And for each example, I want to determine, are the triangles congruent, and if so, why? So in example A here, you'll notice that I have my two triangles. I have one pair of sides congruent, so if I wanted to put a little S in a circle there just to remind myself, okay, there's a pair of sides. Then I have a pair of sides that aren't congruent necessarily, but they are parallel. And then there might be some other things that I can tell about this picture. Like for instance, I might be able to say that this angle and this angle are congruent because they are vertical angles. So there's a pair of angles for each triangle. And then with these parallel lines, that might be hopefully making me think about possible alternate interior angles that are congruent. So in other words, if these are my parallel lines and then this is my transversal, it would make this angle congruent to this angle. So that would give me another pair of angles there. And it would be two pairs of angles and an included side congruent to two pairs of angles and an included side. So that would give me angle side angle congruence. Now there might be another possibility here though, right? Because I could use this as a transversal, which would make this angle congruent to this angle. And now I could have two angles and a non-included side congruent to two angles and the corresponding non-included side. So angle side would also work in that picture. In example B here, we see we have some segments that are marked congruent, and of course we would have these vertical angles here. And so many people are going to be tempted to say that this is side angle side because I have some marks and an angle between them and then some other sides marked with an angle between them. But what we have to realize is that with side angle side is that if one side is congruent to a side on the other triangle and another side is congruent to another side on the other triangle and the angles that are included are congruent, then SAS works. But what we have here are two sides of this triangle are congruent and two sides of this triangle are congruent, and then of course the angles. But I don't have sides from one triangle congruent to sides of the other, so there is no congruence in this picture that we can guarantee. In part C here, I can see that I have a couple right angles, and then I have a couple segments that are congruent. Now when I have right angles, I might be thinking about HL because it's the special reason that we can only use for right triangles. But in this example, I would need the hypotenuse, which is this segment, and I don't know that those two things are necessarily congruent in this particular example. What I do know is that this angle would be congruent to this angle because of vertical angles. Or I could actually say that, first of all, that would give me angle side congruence because I have two angles and a non-included side. But I know that if this segment and this segment are both perpendicular to this segment, then that means that they are parallel to each other, which would mean that this angle and this angle down here are congruent alternate interior angles. So that would mean that angle side angle would also work in this example. In example D, I have a right angle here, which of course means I have a right angle here as well. So now I have two right triangles. The hypotenuse on the one on the right and the hypotenuse on the one on the left are congruent, right? So there's an H and an H for the hypotenuse of each triangle. And then I have this short segment congruent to this short segment, and there's my legs. So these two triangles are congruent by HL, hypotenuse leg. I verified that I have right triangles. I saw that the hypotenuse on each are congruent, and then there's one leg on each congruent to the other. In example E, I have a pair of segments here that are congruent, which are, of course, sides of my triangles. I have a pair of sides here. Oops, I just wrote an A. I meant to write an S. Pair of sides here, congruent. And then, of course, I also always have to watch out for shared parts that would be congruent to each other by the reflexive property. So in example E, I have two triangles that are congruent by side, side, side. Now in this example, in this diagram, you can see that I have four angles that I've numbered, and I'm going to give some information about this diagram and then determine what else would I know. So for instance, in example A here, I said if ER was congruent to EV, then which two angles would be congruent? Well, if those two segments are congruent, it means that this bigger triangle in this picture, triangle ERV, has two sides that are congruent. And according to theorem 4-1, then I would know that the side across from ER so I'm ignoring these two segments in the middle, that would come all the way across here to angle 4, would be congruent to the side that's across from EV, so coming all the way over here to angle 3. Those two angles would be congruent if segment ER and segment EV are congruent. In letter B, I said, well, what if ES is congruent to ET? And the measure of angle 1 is 75, and the measure of angle 2 is 3x. And how could I find x using that information? Well, I know that if these two segments are congruent, then again by theorem 4-1, that would indicate that angle 1 is congruent to angle 2, which means that the measure of angle 1 could be set equal to the measure of angle 2. So now if I come down here and I say the measure of angle 1 is 75 and the measure of angle 2 is 3x, then I have an equation I can solve. I can divide by 3 on both sides, and 25 would be my value of x. In part C, if angle 1 is congruent to angle 2, and ES is 3y plus 5, so this is 3y plus 5 right there. Maybe I can try and kind of write that in. 3y plus 5 there. And ET is 25 minus y, so that is 25 minus y. Then what does y equal? Well, according to theorem 4-2, if angle 1 and angle 2 are congruent, it would mean that segment ES would be congruent to segment ET, because these two segments, ES and ET, are opposite these two congruent angles, which means I could take the length of ES and set it equal to the length of ET. So coming back down over here, I could say that 3y plus 5 should equal 25 minus y. And now I could add y to both sides, and I could subtract 5 from both sides, and what I'd end up with is 4y, these cancel, equals 20. And these cancel. And I divide by 4 on both sides, and y equals 5. Lastly, on letter D here, I'm saying that ER, again, is congruent to EV, and the measure of angle 4 here is 70. What's the measure of angle REV? So what's the measure of angle REV? This angle right up here. What is that angle's measure? Well, if angle 4 is 70 and these two segments are congruent, then I could also put that 70 over here for angle 3. And I know that all three of these angles, angle 3, angle 4, and the angle that I'm looking for up here, they all need to add up to 180. So I can say that 70 plus the measure of angle REV, which I don't know at the moment, all three of those things added together should equal 180. So that means that 140 plus the measure of angle REV equals 180. And now if I subtract 140 from both sides, the measure of angle REV must be equal to 40. Lastly, I have a picture here where I'm going to draw some of these special segments that we've learned about in this chapter. First of all, I'm going to draw the median. I'm going to draw the median from angle X. Well, if I'm going to draw the median, that means I need to know where the midpoint of the opposite side is, because the median is going to go from that vertex over to the midpoint of the opposite side. So I'll just kind of guesstimate here. I'll say that the midpoint maybe is right there. Let's call that point M, and let's indicate that that and that are congruent to each other, so that's the midpoint. Then my median is going to go from X down to that midpoint. So the orange line that I just drew there is my median. The altitude needs to go from X down to this side and be perpendicular, right? And then since this is an acute triangle, I can draw that altitude within the triangle itself. So I'm going to go from X. Oops, I meant to get my line tool. I'm going to go from X. Now I'm not going to go over here where I wouldn't be perpendicular. I'm not going to go over here because I'm not perpendicular. I'm going to try and go straight down. It just so happens like it looks like it's right where I drew that mark. I'm going to go straight down and make my 90-degree angle. So I'll mark that as a 90-degree angle right there. And now the purple segment is my altitude. Next, I'm going to draw the perpendicular bisector of segment ZY. Now the perpendicular bisector needs to be perpendicular to segment ZY and bisect it. Means it's going to go through the midpoint. Well, I've already determined that M right here is the midpoint. So if I'm going to make the perpendicular bisector, I'm going to, get my line tool, sorry. I'm going to make a segment that starts at M, or that goes through M, and is perpendicular to segment ZY. I'm going to make it a little bit longer here. I'll make it go through that side. Notice it doesn't necessarily go over to the vertex here. What it does is it goes through the midpoint and makes a 90-degree angle. Lastly, I'm going to draw the bisector of angle Z. The bisector of angle Z. Let's do that in blue. So angle Z here, it needs to be bisected, means cut into two equal-sized angles. So it looks like if I draw a segment that looks something like that, and that looks to be like it bisected it, but let's just indicate it by putting my two congruent marks there. So angle Z has been bisected. Now I have a couple other questions I want to kind of follow up with on this. If I were to put a point on this perpendicular bisector right here, and let's call that point C, then point C is equidistant from what two things? So this would be where theorem 4-5 comes in. Point C is on the perpendicular bisector of segment ZY. And theorem 4-5 says that any point that's on the perpendicular bisector of a segment is going to be equidistant from the endpoints of that segment. So the endpoints would be Z and Y. So point C is equidistant from Z and Y. Now what if I put a point on the angle bisector right here, this dark blue line that's bisecting angle Z? So let's put a point right about there. Let's call that point D. Point D is equidistant from what two things? This is where theorem 4-7 comes in. According to theorem 4-7, any point that's on an angle bisector will be equidistant from the sides of the angle that's been bisected. So what that means is that if I go from, let me use that blue color again, from D over to this side of angle Z, or if I go from D over to this side of angle Z. Now remember, when I measure the distance from a point to the side, I do it along a line that is perpendicular to the side of the angle. That would mean that these two segments are congruent, or in this case, that D is equidistant from segment ZX and segment ZY. All right? So that's theorem 4-7. All right, folks, so I hope that you have all this stuff kind of straightened out and settled away in your mind. If you do have any questions, of course, you can come talk to me, and I'll try and help you out with anything that's still a little bit shaky for you.